Okay, maybe I can just start with a couple of announcements. Okay, did I spell announcements right? Okay. If your handwriting's bad enough, no one can tell if you misspell anything. That's the trick. Okay, so for the first announcement, I am going to be out of town on Thursday, but there will still be a class, so there's going to be a super secret surprise guest lecture in class at the usual time and place, so that'll be exciting. You should all come. I think you'll enjoy that. The second announcement is that, as I think I mentioned last time, I missed one lecture earlier on in the semester, so I owe you guys a makeup lecture. And so there will be lecture sort of next Tuesday in the usual time and place. So that's the last lecture of the semester. So I guess ostensibly classes are supposed to end on Monday. We'll end a day later, just because so I can give you this makeup lecture. So that's the lecture where we'll sort of wrap up with some nice computations in quantum electrodynamics. The other announcement that I'll give is that I am just handing out a problem set, and so the final problem set is going to be due, so even though I'm handing it out today, it'll be due on Friday as usual. So on Friday, so due on Friday, what is that, December 11th, as usual. I did this final problem set is, well, it's instead of a final exam, so it is a tiny bit longer than usual, but boy, it's a fun problem set. I mean, by the time you've done this problem set, you will really know how to do Feynman diagrams and QED and all of that good stuff. Okay, so you'll really know a lot by the time you're done with that problem set. And then the final announcement, as I think I mentioned earlier, I do encourage you all to register for QFT2, the second semester version of this class. I mean, maybe not this class, but at the final class on Tuesday, I could even give you a little bit of a sort of taste of the sort of things that we might be doing in the second semester. I mean, this first semester is really sort of focused with laser-like efficiency on developing the theory of quantum electrodynamics and all of the various perturbative techniques that go along with the theory of quantum electrodynamics. The second semester really focuses much more, I think, on the conceptual structure of quantum field theory and on more broad applications of quantum field theory. So we'll be doing a lot of study of renormalization group flow, which is kind of the basic way that we think about the applications of quantum field theory more broadly as general theories of particle physics, both of the sorts of particle physics that we might describe when we study elementary particles, but also the sorts of particles that arise in condensed matter systems, phonons, magnons, stuff like that. So we'll be doing some condensed matter theory. We'll be doing what's known as effective field theory, which is the basic strategy that we use to study essentially any theory using quantum field theory, essentially any system using quantum field theory. We'll understand why it is quantum field theory is the universal language for understanding physics at low energies. We'll understand Yang-Mills theories, which are the sorts of theories that arise in the standard model of particle physics. It'll be a good time. You should all take the course. Good. So that's it as far as administrative stuff. My goal today is to continue with our discussion of quantum electrodynamics, sort of picking up where we left off last time. Maybe before I begin with the physics lecture, I can pause and see if there are any questions. Okay, no questions. Good. So we've spent some time in this class learning about how to compute Feynman diagrams, first in simple theories and eventually in more complicated theories, such as quantum electrodynamics. But when we want to compute something physical, we're actually interested not necessarily in a scattering amplitude, but rather in a cross-section, okay, which would be something like a scattering probability. And I just want to remind you of the strategy that we developed last class for computing cross-sections. So the first thing that you do is that you enumerate all of the diagrams that contribute to the scattering amplitude, M, and typically we only want to work up to a certain order in perturbation theory. Otherwise, there would be an infinite number of such diagrams. But at a finite order in perturbation theory, there'll be a finite number of such diagrams, which we can sum up to compute the scattering amplitude. We then square the scattering amplitude to compute m squared. And then, assuming that we don't observe all of the polarizations of the incoming and outgoing particles, we have to sum over the unobserved polarizations. And last time we developed a technique for summing over these unobserved polarizations. So for example, if we have a Dirac spinner, then its polarization is given by one of these four-component spinners U. And when we square, we get both a U and a U bar. And the sum over the polarizations labeled by S, S being an index that runs from 2, is then something that you computed on an earlier problem set this semester. And using this formula, one can go ahead and remove all of the dependence on the polarization in your sum. And you get an expression involving a trace of a bunch of gamma matrices along possibly with things like P slash, so various momenta that will appear in your scattering amplitude. And we worked out an example of this last class when we computed, I guess, did we compute Compton scattering? No, we computed electron-positron annihilation last class. Or maybe we did electron-muon scattering. I don't actually remember what you did. I think on the problem set you're doing electron-positron annihilation. Is that right? You're doing Balois scattering. That's right. Okay, good. So we average over the polarizations of the incoming particles if we don't observe them, and we sum over the polarizations of the final particles. And this is the appropriate formula to use for scattering of Dirac spinners, like electrons and positrons. But if you also have external particles, which are photons, then if you don't observe their polarizations, you'll need to sum over those polarizations as well. And so you'll get expressions in the squared scattering amplitude that look like this. So here you have a sum over polarizations labeled by an index A of a polarization vector epsilon times another times the complex conjugate of that polarization. And as well as you hopefully discovered on your problem set, and as in fact I'll prove to you a little bit more formally using a sort of clever trick today, when you do the sum over polarizations of a photon, you get a very similar formula where you can just replace the square of one of these polarization vectors with the metric. And this is the formula that you would use when you have external photons. And when you sum over polarizations, the end result will be a product of a bunch of traces. So these are traces over various spinor indices, which can then be evaluated using the trace identities that you proved on one of your problem sets to give this squared scattering amplitude as a function of the momenta of the external particles, the ingoing and outgoing particles. And, of course, in addition to depending on the momenta, they'll also depend on whatever polarizations are observed. Okay, so for example, let's say you don't observe the initial polarizations, but you do observe the final polarizations. Then you would sum over the initial polarizations and not the final ones, and you would get some function of the momenta and the final polarizations. So at this point, you have an expression for the scattering probability, the square of the amplitude, as a function of the momenta. And then typically what we do is we then want to write this in terms of some sort of set of kinematic variables which describe the scattering process. Because generally speaking, the incoming and outgoing momenta will be constrained. Among other things, they'll be constrained by momentum conservation. And so that means that if you're studying, for example, 2-to-2 scattering, instead of studying this as a function of 16 quantities, namely the 2 incoming 4-vector momenta and the 2 outgoing 4-vector momenta, using Lorentz invariance, conservation of momentum, and so forth, you can reduce this down to a much simpler set of kinematic variables, such as, for example, the center of mass energy and the center of mass scattering angle in the case of 2-to-2 scattering, or other sort of relatively simple sets of scattering of kinematic variables for other kinds of scattering processes. Okay? So, for example, in a decay process, you might write this as a For more general scattering processes, there'll be more general sets of kinematic variables. Usually, we'll just be considering 2-to-2 scattering. And then finally, what you'll get is a scattering amplitude written in terms of these kinematic variables. And then you have to decide which of those variables you're actually going to measure. And you integrate over whichever variables you don't measure. So the unobserved kinematic variables. So, for example, let's say that you're studying some scattering process, and say it's a 2-to-2 scattering process. So that would be a function of the scattering angle theta. But if you don't measure that angle, you just want to compute the total scattering probability, then you would integrate over it to get the total scattering cross-section sigma total. Okay. So, in general, what I don't want to do is go through this systematic process every single time we have to compute something, because the calculations can get a little bit, they can get a little bit onerous. Indeed, I encourage you to look in the textbook or one of the other textbooks for a few of these calculations worked out in all of their gory detail for the case of Compton scattering, for example, or electron muon scattering or something like that. And it's a sort of a completely straightforward but kind of a long computation. So what I'm going to do today is, rather than going through every detail of these steps, we went through one computation in detail last class where we did this whole polarization sum. Instead, what I'm going to do today is kind of summarize some of the answers for you and discuss their physical properties, which I think is probably a better use of our time than spending 2 to 3 lectures going through all of the algebra to compute, for example, scattering probabilities for Compton scattering or something like that. So I'm just going to focus a little bit more on, the process by which I do it. So outlining this process in detail, making sure you understand it, and explaining a bit of the physics of the answers rather than going through all of the algebra in detail. Because you can always, look that up in your textbook. And you'll get plenty of chances to do the algebra, for example, on your problem sets due this week and next week. Okay, so what I'm going to do now is give you a sort of tour of a few kind of interesting results in quantum electrodynamics using these techniques. But before I do so, let me pause and see if there are any questions. Is there any part of this procedure that is unclear, in principle or in practice? Good. Okay. So let me give you an example. So last time, we computed the probability for an electron-positron pair to annihilate and form a muon-antimuon pair. And we went through quite explicitly and studied the case where we don't observe any of the initial or final polarizations of these particles. So we had to compute this sum. And we obtained some specific, albeit rather complicated answer for the total scattering probability. What I want to do now is I want to rewrite that answer for you, but I'm not going to write it in the form that we wrote it at the end of class last time. Instead, I'm going to write it in the form that we would have if we went and applied all of our hard work for the involving Mandelstam variables and center of mass coordinates to write the answer in terms of the sort of standard phase space variables for 2-to-2 scattering in center of mass frame. So in center of mass frame, the way that you think about this is you think about an electron-positron pair that are coming towards each other with equal and opposite velocity. Then they undergo some scattering process, and out shoot a muon-antimuon, again with some energy, and at some relative angle that we could call theta. So the two variables that we use to characterize this process are going to be the center of mass energy. So in fact, I'll just, to make some of the formulas a little bit simpler, divide that by 2 to write the energy E, which is the energy of one of these incoming particles. So each of these incoming particles have some energy E in their rest frame. And the other variable is, of course, the scattering amplitude. And then if you take the answer that we wrote down last class for the square of the probability m, and then you include the kinematic factors that you need to in order to write this in terms of the scattering cross-section d omega. In terms of these variables E and theta, let me just write down the answer for you. So the first thing that I remind you is that the scattering amplitude was proportional to E squared because there were 2 interaction vertices. So that means that the scattering probability is proportional to e to the 4th. So this scattering cross-section is proportional to alpha squared, where alpha is this fine structure constant, e squared over 4 pi. And then there is some dependence on energy. Okay? So in fact, this dependence can just be worked out by dimensional analysis. Okay? So it goes like 1 over e squared, because the scattering cross-section has dimensions of area, times some dimensionless function of E and theta. And what I'm going to write down for you, just so that you have an idea for what these sorts of functions look like, is the expression that we would get if you wrote down the scattering amplitude in the limit where we take the muon mass to be much greater than the electron mass, so that we can effectively set the electron mass to 0. So when we computed this last class, we kept both the muon mass and the electron mass, just to make things completely precise. But for actual scattering processes that we might be interested in, the muon is 200 times heavier than the electron. So if you scatter at energies that are of order the muon mass, the electron is effectively massless. You can ignore those things, up to errors of about 1% or so. And so this is the answer that you get. And moreover, if you wanted to compute the scattering cross-section, you would integrate this d theta, and you would get an answer. Well, how would you do this? Well, remember that you would have to integrate cosine squared theta, and the measure factor is a sine theta d theta, or a d cosine theta. And so this is something like, 2/3 or something like that. So when you put this all together, you'll get some factors of pi. Did I get that right? Okay. something like that. You'll get some factors of pi, some factor of 3, and you'll get an answer for the cross-section, the total cross-section. That's a function of the center of mass, the energy and center of mass frame of one of these incoming particles. Yes?
I've seen this done before, and it's kind of confused me, but d cosine theta is negative sine theta d theta.
Mhm.
So I'm wondering where that extra negative sign goes away, or if there's some symmetry that allows you to not take that into account when you write d
Well,
cosine theta.
the scattering cross-section is a positive quantity by definition. So if one is ever confused by any of the signs, you can just remember that it's positive. Of course, whether the whether the measure factor has an overall sign in it is, to some extent, depends on your choice of coordinates. Do you take theta to run from 0 to pi, or 0 to pi over 2, or do you take it to run from pi over 2 to 0? That'll should give you an overall sign. So let me put it this way. If you take theta to run from 0, so how do we usually take it? So usually you might take theta to run from from pi over 2 to minus pi over 2. Is that how you would take theta to run? That means cosine, well, you need to be a little more careful. Let's see, if you take as theta, when theta is 0, cosine theta is 1. So if you take theta to run from 0 to pi over 2, how does it work? Cosine squared theta, yeah, actually should be a little more careful here. Cosine squared theta will run from 1 to 0, not from 0 to 1. Okay, so I really should have put a 0 there. So you get a minus sign because you have to switch the limits of integration. Is that clear? I went through that a little bit quickly. The integral that we're doing is an integral where theta goes from 0 sine theta d theta of cosine squared theta. Okay. So theta runs from 0 up to pi over 2, right?
Why is it pi over 2 to pi?
Is it 0 to pi?
Yeah, and it is minus 1 to 1.
Is it minus 1 to 1?
Sign your thetas or your thetas are backwards on the
Yeah.
so you just flip them
Okay. Is it 0 to pi? I guess it is 0 to pi, isn't it? Yeah, I always forget. Yeah, that's right. That's right. It's 0 to pi. Good. Okay, yeah. So, right. So, if you let C be cosine theta, then dC is minus sine theta d theta. But this is now an integral that runs from 1 to minus 1 of C squared dC with a minus sign, right? Coming from that minus sign here. And then you have to reverse the order of integration, so that's the integral from minus 1 to 1 of C squared dC without the minus sign. Good. Is that more or less clear?
Yeah.
Okay. Otherwise known as like 2/3 or something like that. Sorry, it's supposed to be a 2/3. Did I get that right, more or less? Yeah. Good. Questions? Good question. Any other questions? Okay. Indeed, I mean, you can see that going from this expression down to this expression for the total cross-section, all I've done here really is replace that cosine squared by a 2/3. Okay. I mean, it's worth sort of staring at this answer for a second for the total cross-section. So what does that look like? Well, let's just sort of sketch a plot for what this cross-section looks like as a function of energy. So what we're imagining doing is we're imagining some scattering process where you send in an electron and a positron pair. You send them towards each other in their center of mass frame with some energy E. And the first thing that you notice about this expression is that it makes sense only if E is bigger than mu. In particular, the scattering cross-section is going to vanish. And indeed, you can pretty easily imagine that the scatter, just by conservation of energy, if you want to produce a muon anti-muon pair from an electron-positron pair, then conservation of energy says that you need to send these electrons and positrons together with an energy that's at least the mass of the muon. And that's reflected in this formula. And indeed, you see in this formula that scattering amplitude, that scattering cross-section vanishes as E approaches m mu. Okay. So the scattering cross-section is going to be 0 if E is less than m mu. And then it increases as you increase the center of mass energy. And then at high energies, these terms just become very small, and the scattering cross-section will approach a constant. Or rather, it'll approach a constant divided by E squared. So what I'm plotting here is this cross-section times energy squared versus energy. Remember, just by dimensional analysis, scattering cross-section has dimensions of area. Okay. And so scattering cross-section has dimensions of area. So really, it's scattering cross-section times energy squared. That's some sort of dimensionless characterization of the total scattering property, the total scattering area. So the two comments that we'll make is first that there's a threshold for production. Which says that the energy is m mu, or namely that the center of mass energy is twice m mu. And second, that the fact that at high energies the cross-section falls off like 1 over energy squared really is just dimensional analysis. But the coefficient is where a lot of interesting physics happens. So in particular, the fact that the coefficient is proportional to the fine structure constant squared is just because we're doing this annihilation, this scattering process by the exchange of a photon, which has 2 interaction vertices. And then there's a numerical coefficient that depends on the details of the quantum electrodynamics Feynman rules, details that we worked out last class. And indeed, this process, so this process can be measured. It can be measured very, very precisely, and you get a curve that essentially looks exactly like this. And it can be used to give, for example, accurate measurements. I believe the most accurate measurements for the masses of both the electron and the muon. And in fact, processes like this, where electron-positrons bang into each other and annihilate into other particles, are one of the main ways that we observe all kinds of different particles. Okay. So, for example, any particle that has charge can be produced in this process. So, for example, quarks have charge. So you could imagine some annihilation process where an electron and a positron bang into each other at very high energy and then form some sort of quark-antiquark pair. Now, this is the sort of thing that might happen at Fermilab or the LHC or something like that. But of course, as you probably know, free quarks are not observed in nature, unlike muons. So the process of electron-positron annihilation into a mu bar is something that you would actually observe. You might actually observe a muon, or at the very least one of its decay products. But you never actually observe a free quark. Instead, what happens is that these quarks, because of the strong interactions of QED, will quickly be surrounded by a cloud of other sort of particles. They'll form what's known as a jet of hadrons. So you'll get what's called a jet of very massive particles that are formed once these quarks and the quark-antiquark pair is produced via electron-positron annihilation. But nevertheless, this formula that we derived still gives you a very good prediction for the total scattering cross-section for the production of these two jets of hadrons. So, for example, at high energy, what do we expect? We expect that sigma, so we can just read off from this formula at high energy. Okay. So let's imagine now we're studying Q bar production by electron-positron annihilation. So it should go like 1 over e squared, 1 over the center of mass energy of the electrons and positrons, just by dimensional analysis. You have this coefficient here. I wonder if I got that coefficient right. Okay, you have some coefficient here. So you got, what was it? So you had a 1 over e squared. The coefficient was pi alpha squared over 3. Is that what the coefficient was? Now, that alpha squared described the, that was the coupling constant in quantum electrodynamics, which depended on both the electric charge of the electron and the electric charge of the muons. Now, quarks have different electric charges from the muons, and so you need to include the fact that the quarks have different electric charges. So you'll need to include a factor of q squared, where q is the electric charge of the quark that you're considering. So it could be 2/3 or minus 1/3 or something like that. There's going to be a q squared there rather than a q to the 4th, because remember we have 2 interaction vertices that are proportional to the charge of the electron and 2 interaction vertices that are proportional to the charge of the quark. Remember, in the scattering process, you get 1 factor of E coming from the coupling of 2 electrons to the photon, and 1 factor of E coming from the coupling of 2 muons to the electron. So when you square that, you'll get a factor of q squared, the quark charge squared. And now the only thing that we need to think about is we need to think about what sort of variables we should sum over, because we're not observing the individual quarks. What we're actually observing is a jet of hadrons. So in particular, you need to sum over all of the possible quarks that you have that could be produced in this process. And in fact, there's one other object, one other observable that you're not measuring in this process, which is the color of the quarks. So quarks come in 3 species, typically referred to as color. And so you're going to get an overall factor of 3 coming from the fact that there are 3 different kinds of quarks, red, blue, and green, and you're not measuring the color of those quarks. So this is the sort of expression that you would get for Q bar production at, say, an E plus E minus collider. This 3 coming from the color of the quarks, which is unobserved. And the important point is that when we do this sum, we should sum over the possible species of quark which could be produced. What do I mean by that? Well, there are many different kinds of quark. Well, not many. Well, 6 is many. Okay, 6 is many. So there are many different kinds of quark, and they have various different masses. And if the energy is E is large compared to one of those masses, then you'll be able to produce the quark. But as we saw up here, if the energy is less than the mass of the particle that you're trying to produce, you won't be able to produce it. So what does that mean? That means that if you want to understand what this scattering amplitude looks like, or the scattering cross-section looks like, as a function of the energy, then what you expect is that it's going to be this sigma times E squared is going to be approximately constant, except it's going to have some jumps whenever it's possible to produce a new species of quark. So, for example, let's say that one of the quarks is the charm quark. Okay. Then there's going to be some sort of jump when the energy in the center of mass frame is the mass of the charm quark. And then there's going to be another jump at the mass of the next quark, which would be the bottom quark, and so on and so forth. Now, in fact, if you look at the data is actually a pretty good approximation for this formula. There are a couple of subtleties, though, which is that in addition to there being free quarks, there are also bound states. Things like psi, j psi, various different sort of quark bound states into which these electrons and positrons can scatter. And so you're going to get little spikes. So this is the sort of overall picture for jet production, but you'll also get little sorts of spikes corresponding to other sort of bound states. So in particular, if you think about, if you actually look up the data, so there's a nice plot in the text in Peskin where he actually plots this data. And it fits pretty well this picture, where you have these sort of plateaus where the cross-section times energy squared is approximately constant. And then there's a sudden jump when you go through one of the quark masses, and then there's another plateau, and then there's another jump. And then there are all sorts of little tiny sharp peaks whenever there's some particular bound state into which these quarks can scatter. And the final question I'll mention is that, in fact, the numerical coefficients here, the values of these constants can actually be measured to quite good accuracy, reasonably good accuracy. And it provides a check on things like the number of colors right here, as well as on the charges of these various quarks. So this is an example of how this sort of QED cross-section might be used to actually understand something about particle physics. Okay. So I'm going to move on to do another example, that of Compton scattering. But before I do so, let me pause and see if there are questions.
Consider a broad one, but what can quantum field theory describe? Does it describe bound states at all?
Absolutely, 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 yeah.
It's so localized, but it's still possible.
Well, let's put it this way. When we talk about elementary particles, we have to be sort of, okay, quantum field theory is a theory of, can be used to describe any localized excitation. And if you have a bound state, and you study the theory on energy scales that are very low compared to, say, the binding energy, or in length scales that are large compared to the size of the bound state, you can effectively treat it as a particle. Okay? So for example, when we studied Yukawa theory of weak interactions, I introduced the pion field, which was the scalar field that mediated the nuclear interactions. That pion field is actually a bound state. Okay? It's not an elementary particle. And frankly, neither were the protons and neutrons, okay, that we were studying. But even though they were bound states, we still treated them as particles. And at low energies, that was a good approximation.
Does it have some ability to discuss, like, to treat the bound state from the field that is constructed that way?
Absolutely, absolutely, absolutely. So that's what I was going to get to. So then, once you crank up to higher energy, these things fall apart into their constituent objects. And you have to think about, and in principle, and indeed in practice, it's possible, for example, to start with a complete theory at high energies, say a theory of quarks and gluons, okay? And then to look at the theory at low energies, ask what the spectrum is, and see that the spectrum is not actually free quarks and gluons, but actually has some complicated bound states at low energy. In general, of course, those are difficult questions to answer precisely, which is one of the reasons why quantum field theory is hard. And this semester, we've sort of primarily focused on the quantum field theory techniques that are valid when you have free particles, as opposed to particles that are strongly interacting at low energies. But indeed, life is not always so simple. Like quantum electrodynamics happens to be a nice theory in the sense that the coupling constant is very small at low energies. So particle interactions are weak, and you have to worry too much about bound states. But you know, that's just quantum electrodynamics. So for example, I could have also computed here. I didn't for the sake of time, but I could have also, for example, one great computation in quantum electrodynamics would be to calculate the lifetime of some unstable bound state. Okay, so for example, you could think about, I think it's positronium, which is E plus, E minus, a hydrogen atom is, it's positronium is a hydrogen atom, except instead of a proton, you have a positron, okay? And so that means that you have an electron-positron pair in some sort of unstable bound state. And you can calculate the lifetime of positronium using precisely these same sorts of techniques. It gets a little bit complicated because you have to talk about whether, just as the hydrogen atom has a spectrum of S wave, P wave, and so forth, you have to talk about which wave function, which bound state of positronium you're talking about in order to calculate the lifetime. So it's kind of like a bit of a non-trivial calculation. It was sufficiently non-trivial that I didn't give it to you on this problem set, but I thought about it. Okay. So yeah, good. Excellent question. To some extent, you might ask, how precisely would we define a bound state in quantum field theory? To some extent, you would define a bound state as a pole on a scattering amplitude. That's as good a definition as any. And it's not an accident that I drew all of these bound state spikes very close to the dotted lines where the masses of these particles appear. Why is that? Well, let's say that this is the mass of a charm. Then you could look for a charm bar bound state. And what is a bound state? A bound state is when you take two particles and you construct a state with energy slightly less than the sum of those two particles, because you have to subtract off the binding energy. And so that's why typically these bound state peaks will appear right before these shifts between the plateaus in the scattering cross-section. So for example, these bound states over here would describe charm bar bound states. These might describe BB bar, stuff like that. Look at the particle data book. It's like as thick as a telephone book, and it's full of these sorts of bound states. Excellent. Any other questions? Good. Okay, I want to do one more example. And this is really the final example that we're going to be considering in this class of a scattering cross-section in quantum electrodynamics, at least at tree level, which is Compton scattering. So that's scattering of a photon from an electron. So what is the sort of process that would contribute to this? So let's imagine that we have an incoming photon and an incoming electron with momenta k and p, respectively, and outgoing momenta p prime and k prime, respectively. Then this is one of the tree-level diagrams that would contribute to this process. There would be some internal so note that I've drawn the arrows moving from left to right because I have an incoming electron and an outgoing electron. And so that means that the intermediate particle by charge conservation has to be an electron in this process. And its momentum is just p plus k, just by momentum conservation. And so we can now go ahead and use our Feynman rules to write down this scattering amplitude, this contribution to the scattering amplitude. So let's just go ahead and do that. So this is an exercise in applying the QED Feynman rules. So let's start by thinking about the spinor polarizations. So we need to start with the polarization of this guy here. So we get a U bar P prime for the outgoing electron. Then you have this vertex here, okay, so that you'll get a factor of minus IE gamma mu coming from that vertex. Then you have this propagator here, which is I over P slash plus K slash minus M. But rather than writing inverse gamma matrices, it's easier to just write that as I p slash plus k slash plus m over p plus k squared minus m squared. Okay. So that's this propagator here. Here, of course, that is just the same as I over p slash plus k slash minus m. I'm just moving that p slash, I'm just multiplying the numerator and denominator of that expression by p slash plus k slash plus m in order to get something that only has all of the gamma matrices in the numerator instead of the denominator. Then you have that interaction vertex over there, so that'll be a minus IE gamma nu. And then you have the incoming electron polarization, so a U of P. Okay. Now we need to take into account the polarizations of the photon. So I suppose I really should have put in that polarization earlier. So you get an epsilon mu of K prime, which is the polarization of the outgoing photon. Note that that mu here is contracted to this mu here because that gamma mu was this vertex, and the gamma nu connects to that vertex. So we have an epsilon nu of K right there. Good. Any questions on that? Yes.
Wouldn't these times at the right is the...
Right, good. So remember, the reason that these scattering amplitudes are all scalars. Scalars all have the form of like psi bar matrix psi. Okay, and so remember that it's the when you have the charge lines pointing out of the diagram that you get a U bar or a V bar, and when they're pointing into the diagram you get a U or a V. So this is the only way that I could have done it and gotten a Lorentz scalar. Good question. Yes.
I think your first polarization for the photon should be conjugated.
Oh, yes, I'm sorry. Conjugate. Thank you. Good. Okay. Paying attention. Good. Similarly, there's one other contribution to this process, which is the T-channel process. Which looks like that. So here, the electron that's connecting these two vertices has a momentum that's determined by momentum conservation to be P minus K prime. Just because we're normalizing we're using the convention where all of our incoming and outgoing particles have a momentum that points to the right. And then we can go ahead and use our Feynman rules to write down this expression. Okay. So what do we get? We get a U bar of P prime, let's call this guy, say, gamma nu. Let's call that index gamma nu. So we get a minus IE gamma nu. We get the propagator, which is P slash minus K slash prime plus M over P minus K prime minus M squared. Then we get this interaction vertex down here, so we'll call that index mu. So we get a minus IE gamma mu, and then we get a U of P. And now we have to take into account the initial and final polarizations. So you get an epsilon mu star of K prime and an epsilon nu of K. Good. Notice what I've done here is I've chosen cleverly my mu and nu indices so that they always multiply epsilon mu star of K prime, epsilon nu of K. That will allow me to easily combine these guys to get the total cross-section, so the total scattering amplitude, which is the sum of these guys. So what do you get? Let's see, you get a minus sign from squaring two factors of I. You get an I from the propagator. You get an E squared, because there are two interaction vertices. you get two polarizations, an epsilon mu star of k prime and an epsilon nu of k. And then you get a u bar of p times, well, from this expression up above, what do you get? You get a gamma mu p slash plus k slash plus m gamma nu over p plus k squared minus m squared. And then finally you get a gamma nu times p slash minus k slash prime plus m gamma mu over p minus k prime squared minus m squared times u of p. And if we wanted to, we could simplify this a little bit. So those denominators can be simplified by noting that, well, what is p plus k minus m squared? Well, that's p squared, which is equal to m squared, okay, which will cancel that minus m squared, plus 2 p dot k plus k squared, but k squared is 0 because the photons are massless. You know, p squared is equal to m squared and k squared is equal to 0. The external particles are on shell. They solve the equations of motion. And similar, p minus k prime squared minus m squared is 2 p dot k prime. So that's one simplification that we can do. Minus, thank you. The other simplification is that we can use the fact that these external, we're contracting with external polarizations, but the external polarizations solve the equations of motion. Okay? So in particular, what is the equation of motion that's obeyed by, so what is u? U is the thing that obeys the equation of motion, the Dirac equation in momentum space. So it's annihilated by p slash minus m. Okay? So if we can take, for example, that p slash and move it to the other side of that gamma nu, then we could use this equation here in order to simplify the expression. So that's what we're going to do. So you'll get something like p slash plus m gamma nu times u of p. Well, what is that? Well, remember that we can always anti-commute p slash through a gamma mu, okay, because the gamma matrices anti-commute with one another, at the cost of introducing the anti-commutator, which was the metric, which will give you a factor of p nu. And then, well, we have that gamma nu times m acting on u of p. And then we can just use this equation here, which says that this term cancels that term. So this is just 2 p nu u of p. Okay. So we can then go ahead and use these guys to simplify our expression for the cross-section. So we get an epsilon mu star of k prime, epsilon nu of k, and then we have a u bar of p prime. And what do we get? Well, we get a gamma mu k slash gamma nu plus 2, let's see if I did that right. Yeah, okay. Gamma mu p nu. That comes from moving this p here through that gamma matrix using this formula here. All divided by 2 p dot k. And then you have a similar expression. Okay. So you have this expression here. So what did you get? You get a minus gamma nu k prime slash gamma mu plus 2 gamma, is it gamma mu p nu? No, gamma nu p mu divided by minus 2 p dot k prime times u of p. All right. Any questions on these manipulations? Now, if we wanted to, we could just go ahead and continue working this out explicitly. But what I want to do is, so one of the things that you proved on your problem set, or rather you discovered on your problem set, is you discovered this rule that when you sum over the polarizations of an external photon, essentially that means you can replace that sum of epsilon, epsilon star by a metric. So I just thought I would go ahead and prove that to you. And rather than doing the computation explicitly, which is what you did on your problem set, I'm going to show you a very clever way to see this almost immediately. Maybe you figured this out on your problem set, but maybe you didn't. But any questions before I do that? Okay. And it'll introduce a sort of beautiful, beautiful piece of physics involving scattering with external photons. Okay. So here's the trick. So let's consider some sort of scattering process. And I want to consider a scattering process with an external photon. Could be either an internal photon or an external photon. So this is the scattering process. So this photon comes in, and then out come a bunch of other particles. Those other particles, some of them could be photons, some of them could be electrons, whatever. You could also have other incoming particles. You could have other incoming photons, other incoming particles, whatever. But I just want to consider one external leg. And when you compute the scattering amplitude, before you contract with an external photon, that scattering amplitude will have an index mu that reflects the fact that you're putting in a vector with some free index. Okay? And so that scattering amplitude is going to take the form of epsilon mu times your scattering amplitude, which has an index mu. So here, epsilon mu is the polarization of your external photon. And what I would like to do is I would like to think about the properties of that scattering amplitude m sub mu. And what I would like to understand is what properties gauge invariance imposes on that scattering amplitude. In particular, what we're thinking about here is we're thinking about a process where you send in a photon with some polarization epsilon mu. But I want you to remember that the definition of a photon is something that's kind of ambiguous because of gauge symmetry. And in particular, under a gauge transformation, how does your electromagnetic potential change? Well, it changes by the addition of a total derivative. So this is how a mu of x changes. But you could also consider the Fourier transform of A. So the Fourier transform of A, so if you think of A, the Fourier transform of A as a function of the four momentum, how does it transform? Well, the derivative, so you could think about the Fourier transform of your gauge function lambda. And then the derivative of that, well, a derivative in momentum space just means you multiply by the 4-vector k. So what does that mean? That means that under a gauge transformation in momentum space, A goes to A plus k. And what was the polarization? Epsilon was literally just a mode of the electric field in momentum space. Epsilon is literally just A in momentum space. So that means that, because A goes to A plus k, so the polarization vector epsilon will go to epsilon plus k times your arbitrary gauge parameter lambda. But remember that these gauge transformations can't change the outcome of any physical process. So we have a little bit of a puzzle here, which is that you have the scattering amplitude, okay, which depends on epsilon, But epsilon's not even defined except up to shifts by k. You know, epsilon and epsilon plus k really are just different ways of viewing the same thing. So how could this puzzle possibly be resolved? It would appear that but you could do a gauge transformation and you would get a different answer for the scattering amplitude. And the only way that these scattering amplitudes cannot destroy this gauge symmetry is if these scattering amplitudes m have the property that m mu contracted with k mu must be equal to 0. So this means that for any scattering process with an external photon, if we replaced epsilon by k mu, the amplitude would be 0. And this is a sort of remarkable consequence of gauge invariance. And it's something which is known as the Ward identity. Essentially what it means is that when you start computing things quantum mechanically, this gauge symmetry is going to remain unbroken. And if you found some sort of scattering process where k mu contracted with mu was not equal to 0, that would mean that quantum mechanics has broken your gauge symmetry. Now, one of the remarkable things about this is that these Ward identities are true in quantum electrodynamics. Your gauge invariance persists even at the quantum mechanical level. Okay. But in quantum electrodynamics, these Ward identities follow from cancellations between different Feynman diagrams. In particular, if you look at the two processes that we've considered up here, these are two different processes that contribute to Compton scattering. And if you looked only at the S channel or the T channel scattering amplitude, this Ward identity would not be true. It only follows when you do it when you add the total of these two together. Okay? It's kind of remarkable. And you know, just if I can give a sort of wax philosophical for a second, you know, what does this mean? This means that you have a symmetry in your theory, but it's a symmetry that's not being respected by the computational method that you're using to actually compute things. Okay? So to some extent, what's going on here is that you have a property that must be held by the final answer, but the intermediate steps in your answer do not obey that property. But you know that because of symmetry features of your problem, that property has to be true at the end of the day. So to some extent, this is a hint that Feynman diagrams are not the most intelligent way of organizing perturbation theory for theories with gauge symmetry, for things like quantum electrodynamics. And that there may be different ways of organizing perturbation theory and quantum field theory which respect the fact, where you wouldn't have to follow, you have to cancel Feynman diagrams against one another in order to rediscover this gauge symmetry. Essentially, some way of saying that slightly differently is that when you use the Feynman diagram expansion for quantum field theory, the intermediate steps in the calculation are more complicated than they have to be. So in fact, I think one of the sort of main subjects of research in quantum field theory nowadays is to try and find other techniques for computing scattering amplitudes and gauge theories which respect this gauge symmetry at all of the intermediate steps of the calculation. Okay. So this is sort of cutting edge stuff. It's not something that we're going to comment on too much, but it's a remarkable fact that when you do sort of more sophisticated scattering calculations and theories with gauge symmetry, you end up with crazy expressions where people do calculations where they add together 100,000 Feynman diagrams. Each individual term is incredibly complicated, and if you wrote it out naively, it would take pages and pages and pages. But then it simplifies down to an expression that, you could write on the back, that you could write in one line, or a half of a line, or a tenth of a line, or something like that. There are all sorts of hints that the language of Feynman diagrams, as beautiful as it is really not the correct way to think most efficiently about a lot of sorts of symmetries that arise in physics. So that's just sort of an advertisement. But instead of trying to understand those fancy new techniques, let's understand the dumb old techniques. Okay? And so in particular, what we could do is we could check explicitly, maybe this would be a fun exercise, we can check explicitly that these Ward identities are satisfied for this expression for the scattering amplitude. Okay. Any questions on this before I continue? All right, I'm going to be a little late. Yeah. So maybe we'll just leave this as an exercise. Because unfortunately that would take too long. That this scattering amplitude that we wrote down above, if you replaced epsilon with k, you just get 0. Okay. It's a straightforward manipulation, okay, using gamma matrices and gamma matrix identities, and not something I think that I'm going to go through in detail. But I'll just say that it requires one to take into account the full answer involving both the S and the T channel Feynman diagrams. Okay. Good. Okay. So why did I go through all of this business with this Ward identity? So for the scattering process that we're considering, let's imagine that we do a scattering process where we don't measure the polarization of the photon, either the initial or the final polarizations. And so that means we have to sum over these polarizations. So that means that in our expression for this scattering amplitude, so let's say that we have some sort of scattering amplitude where we have some incoming particle, photon, with a particular polarization and momentum. And we might have some other sort of particles, photons, or positrons coming in or out like this. But let's just focus on one of these indices. Then you'll get something like a sum over polarizations of epsilon mu of k contracted with the amplitude m mu. That will also depend on k. And we'll have to square it, okay, where we sum over the polarizations, which we could call S, where S is an index that runs from 1 to 2. Or if we wanted to write that out a little bit more explicitly, it would be the sum of epsilon mu star of k, epsilon nu of k, m mu of k, m nu star of k. Oops, sorry. Got my stars in the wrong place. Okay. So let's just understand in a little bit more detail what this sort of expression might look like. So let's just take a very simple example. Let's just work in a frame where our photon is moving in the z direction. So if k squared is equal to 0, this is the most general form that I can write for the photon's form momentum. And then the two polarization vectors that we could be interested in, we could work with linearly polarized light. So there would be polarization in the x direction and polarization in the y direction. And then this sum over S of epsilon m squared, what is that? Well, that's m1 squared plus m2 squared. Okay. All I'm doing is so m1 and m2 are the first component of the vector mu. The 1 and 2 components of the vector mu. Okay. Is that clear? I mean, I haven't really done anything yet. Okay. But we can now use the Ward identity. So k mu mu is equal to 0. What is that? Well, just using that explicit form for k mu, that says m0 is equal to m3. So in this expression here, I can play my favorite game of adding 0 to this expression, but 0 written in a very fancy way. In this case, 0 is equal to m3 squared minus m0 squared. And what is that? Well, that's minus g mu nu, m mu, m nu. Yes?
How do you know your polarizations are transverse to your direction of travel if you're not in the lens gauge? Like in this case, how do we know that they're transverse?
Well, you can always choose them to be transverse.
Do we mean like are there too many choices, or how do you know that this is Feynman still, or Feynman case that we chose at some point? Or you just need to choose them to be
Yeah.
orthogonal?
You just need to choose them to be orthogonal to each other. You can always shift them to add something proportional to k. Okay, that's the choice. That's the gauge. The gauge symmetry, remember, is shift, as we just saw earlier. Gauge symmetry is shift of epsilon proportional to k. Okay, but k dot epsilon equals 0 is the equation of motion. Good question. Okay. So thus, when we sum over polarizations, we can always replace the sum of epsilon mu, epsilon nu star with a factor of the metric. Okay? And this is something that you hopefully discovered on your problem set. And now you can see here that the fact that this was true for that amplitude that you were considering in scalar QED, I think it was in fact a consequence of the fact that your amplitude obeyed the Ward identity. Although you probably weren't thinking of it in these terms. Okay. So given this, it's now straightforward, okay, and I'm going to put straightforward in quotes because, well, first of all, I can't spell straightforward. It's straightforward to compute the scattering amplitude. In particular, we compute the sum over the external polarizations, both of the photon and of the fermions, and to find the scattering amplitude, and write that in terms of our favorite kinematic variables. Now, I say it's quote-unquote straightforward. It's sort of interesting. You know, if you look in the textbook, he actually does this calculation. He does most of it. He skips a bunch of steps, but he does most of this calculation. It takes just several pages of algebra. You know, the quote he uses is quote-unquote, you know, what did he say? He says, after the smoke clears, one gets this expression. And then I looked in one of the other textbooks that I recommended to see if he worked it out explicitly. And he said, what did he say? He said, it's a bit of a mess, but after some algebra, ... this is the expression. Okay. So what I'm going to do is I'm going to say it is now straightforward, ... to go ahead and compute this expression. You know, I don't think that you would necessarily benefit from my going through all of the algebra in a huge amount of detail. So I'll just write out the answer. Okay. So what are the kinematic variables that we're going to use? So if we study 2-to-2 scattering of massive particles, then it makes sense to work in a center of mass frame. But when you study the scattering, Compton scattering, it's a little bit more typical to use what's known as a lab frame. So in lab frame, you imagine that you have some particle at rest. Your electron is sitting here at rest. Okay? So its form momentum is just m, and is just equal to m(0,0,0,0). And your initial photon form momentum is omega 0, 0, 0. And then after the scattering process, your electron will be moving off at some form momentum, p prime, and your photon will have scattered at some angle theta, and so k will be given by some frequency omega prime, and the scattering will take to be in the xz plane, okay, just by a choice of coordinates. It's really a choice of what we mean by the x-axis. And so then you can go ahead and compute the scattering amplitude in terms of the frequency of the incoming photon and the scattering angle theta. So just as in center of mass frame for 2 to 2 scattering, we often use the center of mass energy and the scattering angle. Here, in Compton scattering, it's typical to use the frequency of the incoming photon along with the scattering angle theta. So one exercise, and this is just a consequence of special relativity. It's just, you know, this is a problem that I assign in my modern physics class when I teach sophomore special relativity. You can go ahead and compute omega prime in terms of omega and theta. And the answer is given by Compton's famous formula, okay, which says that if you have Compton scattering of a photon off of an electron, the change in frequency of the photon is a function of the scattering angle, and it's 1 over m times 1 minus cosine theta. Okay. You may or may not have already rediscovered this formula in the problem set on Compton scattering and scalar QED that I gave you. Did you all more or less discover this formula? Okay.
We were at center of mass frame.
Oh, did you do it in center of mass frame, not lab frame? Okay. Maybe next year. See, this is why the people in future years always have it better. Maybe next year I'll have you guys have them do it in lab frame. Okay. So this is Compton's famous formula. It's almost trivial. I mean, it's just literally, you know, it's just literally conservation of form momentum. What we can do now, now that we have quantum field theory, is we can compute not just the change in the frequency as a function of theta, but we can compute the intensity of the light emitted as a function of theta. Okay? And so this is the calculation that you'll get to after the smoke clears and the dust settles. It's straightforward to see that you get an answer for the scattering cross-section. So what is it? Again, it's proportional to alpha squared. Okay. Just because you have 2 to 2 interaction. So you get 2 factors of the electric charge in the scattering amplitude, which squares to give you an e to the 4th, or an alpha squared. It goes like 1 over energy squared. Okay. So it has to go like 1 over m squared just by dimensional analysis because it has units of area, where m here is the mass of the electron. And then we get something which is a function of the frequency omega and the angle theta. Okay. And this is an answer which is known as the Klein-Nishina formula. I'll just write it down for you. It's one of those deceptively simple formulas. You know, you would think that, well, you know, all we have to do is we have to take this quantity here. What do we have to do? We have to square it. We have to sum over the polarizations of the two photons, k and k prime, sum over the polarizations, so epsilon k and epsilon k prime. We have to sum over the polarizations u of p and u of p, u bar of p prime of the initial and final electrons. You get a bunch of traces involving gamma matrices. You just have to do the algebra and sum it. You know, you get you get 4 different terms here because you have to square this sum of 2 terms here. You know, it's just a bit of a mess. But when you do it, the answer that you get is quite simple. It's known as the Klein-Nishina formula. And it gives you the expression for the intensity of light which is scattered by an electron as a function of the scattering angle. Okay. So this is the intensity of light as a function of the scattering angle. And just for historical purposes, I'll mention that there's one sort of interesting limit, which is the limit where we take the electron to be very massive. Okay? So if m is very heavy, then just looking at Compton's formula here, you see that omega is very close to omega prime. Okay? And so in that limit, omega over omega prime is very close to 1. And we get what's known as the formula for Thomson scattering, which has a very simple dependence on angle. So in this limit, the dependence on frequency has completely disappeared. And you get an expression for the intensity of scattered light, which is just a very simple function of the angle of scattering. It's 1 plus cosine squared theta. And this is one of those subjects where every formula you write down has another name and probably another Nobel Prize associated with it. I don't know if Klein probably won a Nobel Prize. Let's say he won a Nobel Prize. And this just about wraps up what I wanted to say about various cross-sections in quantum electrodynamics. Just to set the stage, we've done so far in this course a lot of calculations for quantum field theory at tree level, that is to say without studying loop interactions. What I wanted to end with next class is our first example of a loop diagram in quantum field theory. And in particular, what we're going to do is we're going to calculate the anomalous magnetic moment of the electron. Okay? I think I can do it in one lecture. We'll see. And this really will serve both as kind of the high point of our discussion of quantum electrodynamics. It's probably the most important single computation in quantum field theory, as well as probably the best measured quantity in physics, and certainly the most impressive match between experiment and theory, maybe in the history of science, certainly one of the most impressive in physics. And it will also serve kind of as an invitation to some of the things that we'll be discussing next semester. Good. Okay. Any questions before I end? Good. Okay. See you not on Tuesday, but see you not Thursday, but Tuesday.